Hello from Force. Welcome back for our third lesson in electrochemistry. Last time we looked at redox reactions, but our discussion was based on oxygen transfer. Then we went ahead and also looked at redox reactions based on electron transfer. We did two examples, that is, and we were in the process of looking at the third example, which is the last one, before we stop. So let us pick it from there and move on. The objective of our lesson today, that is one, at the end of this session, we should be able to actually give further examples or more examples of such reactions. And then two, you should be able to define oxidation number. And three, should be able to calculate oxidation numbers of elements in combined state. So let us move on with our third example on redox reactions. Now, the third example that we are going to use is a very common equation. And that equation that our discussion is going to be based on today is redox reaction involving acidified potassium dichromate 6. Now, acidified potassium dichromate 6 dissolve in water to give potassium ion, that is 2 potassium ions, and the dichromate 6 ion. Now, if, for example, you are reacting it with iron 2 sulfate, then iron 2 sulfate solution contains iron 2 ions and sulfate ions. And then we are talking about acidified. In this case, we are going to use an acid, and in our equation, we will use hydrogen ions to symbolize an acid. Remember, acids are substances that dissolve in water to give hydrogen ions as the only positive ion. The potassium ion and sulfate ions do not participate in this reaction. So we are going to ignore them. We are going to ignore sulfate ions and the potassium ion. And therefore, let us come up with an equation to show that the reaction between acidified potassium dichromate 6 and iron 2 sulfate is a redox reaction. That is what we want to show here. Now, in showing that, we will start by having our iron 2 ions being oxidized by losing electron to form iron 3 ion. As I said last time, that loss of electron is actually oxidation. So moving from iron 2 to iron 3, you have to remove one electron. If you missed the last part where I explained this, make sure that you watch the last video. Now, dichromate ion. The dichromate ion, in the presence of an acid, will change to this chromate ion will oxidize the hydrogen ion to form water. And then we will remain with chromium 3 ions. We balance oxygen. We have 7 oxygen on the reactant side. This side we have 1 oxygen. So we make oxygen to be 7. Hydrogen is 7 times 2, which is 14 hydrogen. We make this one to be 14. Then finally, we balance chromium. We have 2 chromium atoms you must have 2 chromium ions. Then lastly, you must also balance the charges. This side we have -2. Here this is +1 times 14, +14. +14 minus 2, +12. So on the reactant side, we have +12. 12 positive charges. We move to the other side. 2 times +3 is +6. +6, 7 water as a 0 charge, it is a molecule. So 7 times 0 is 0. Now the overall charge this side is +6. Now this side we have +12, this side we have +6. We must bring this one back to +6. So that we have +6 this side, +6 this side. For us to bring this one back, to bring this one down to +6, we must subtract 6. Because 12 minus 6 will give us +6. These 6 negative charges are related to what? Are equal to electrons. So we need 6 electrons. Why? Because 1 electron is equivalent to 1 negative charge. So if I want -6, then I will have 6 electrons, which is equivalent to 6 negative charges. So on this side, the side of the reactants, we must add 6 electrons. We must add 6 electrons. We are through with that. Now this equation is balanced in terms of atoms and in terms of charges. Then, if 6 electrons are gained by what? The dichromate ion. It means 6 electrons must be lost. If 6 electrons are gained from where? From ion 2, then it means 6 electrons must be lost. If 6 electrons are lost, then we need 6 ion 2 ions to lose 6 electrons to form 6 ion 3 ions. Then we add the 2 equations. Meanwhile, this one is aqueous. This one is also aqueous. This one, the state symbol is aqueous. Water is a liquid. Now we add the 2 equations. In adding an equation, you group the reactants together on the left-hand side and the product together on the right-hand side. So our first reactant is 6 ion 2. Our second reactant is the dichromate 6 ion. The other reactant is 14 hydrogen ions. The other reactant are the 6 electrons. On the other side, what do we have? We have 6 ion 3. 6 ion 3. On the other side again, we have 6 electrons. Then we have 2 chromium 3 ions plus 7 water molecules. Those are what we have. Then we remove what is common on both sides. What is common are the electrons. 6 electrons will cancel 6 electrons. So if 6 electrons cancel 6 electrons, then we will remain with 6 ion 2 plus the chromium dichromate ion plus 14 hydrogen ions. 14 hydrogen ions to give what? 6 ion 2, not 6 ion 2, but now it will change to ion 3 plus 2 chromium 3, and then plus 7 water molecules. 7 water molecules. So these are the state symbols of the reactants and the products. So from here, loss of electron, ion 2 loses electrons to form ion 3. Loss of electron is an oxidation process. Then the dichromate 6 ion gains electrons to form chromium 3. So gain of electron is reduction. And therefore we can conclude that the reaction between ion 2 and acidified potassium dichromate involves both oxidation and reduction taking place simultaneously. And therefore this equation here, our final equation, represents a redox reaction based on electron transfer. Remember, this is one of the reactions that is used to demonstrate redox titration in Form 3. And it is an equation that you have met most of the time while dealing with the redox titration. That one brings us to the last example of redox reactions based on electron transfer. The other reaction that is used to show that redox reactions also involve transfer of electrons is where we have ion 2 salt reacting with hydrogen peroxide as shown on the screen. So this one is another reaction. Make sure that at your own time, try and derive that equation the way we have done here so that you can show the two equations and also to prove that this one is a redox reaction. I want you to note certain points here. That one, like while you were doing this, you realize that we had to balance. We had to balance the electrons. And that one brings us to the first point, which is very important, that the number of electrons donated must be equivalent to the number of electrons accepted. That is a very important point, that while writing these equations, the number of electrons donated during oxidation process must be equivalent to the number of electrons accepted. The second point, which is also very important, is that sometimes during displacement reactions, the first example that we used under transfer of electrons was a displacement reaction. During displacement reactions, normally there are some physical changes that takes place, like for example, deposition of solids or change in color or production of gases. So sometimes we have various changes that occur or that accompany redox reactions. And then again, displacement reactions also involve changing temperature, like you have seen under the topic of thermochemistry, that we have enthalpy change for displacement. So most of the displacement reactions are accompanied by what? Change in temperature. Either temperature is released or absorbed. And then another point that you need to note is that the higher the metal in the reactivity series, the higher the enthalpy change or displacement. When, for example, to stress on that point, just to help you understand that point, if you look at the reactivity series where we have potassium, sodium, calcium, magnesium, and then we have things like aluminium, zinc. Now, take for example a displacement reaction between zinc and calcium. Because the two metals are close in the reactivity series, the heat change will be small than when you react maybe potassium and zinc. So if the displacement reaction involves potassium and zinc, the heat change will be large. But where the two metals are close, the gap is not wide in the reactivity series, the heat change will be small, not as large as where the reactivities are quite different. Now, we are moving to the fourth definition of redox reactions, and that one is based on change in oxidation numbers. So in our second segment, we will consider redox reactions based on change in oxidation numbers. Otherwise, thank you for listening. Wait for the next segment.